We continue with the lecture in natural language processing, and we continue our discussion on Argmax based computation, which we have remarked is the foundation for many tasks in statistical natural language processing. Given a problem, many times we formulate this as computation through an Argmax function. Okay. So, we proceed and we are discussing 5 problems in natural language processing, which are modeled through the noisy channel and Argmax based computation. We also remarked that Bayesian decision theory is at the heart of this kind of computation. Given the random variables a and b, P a given b, which is the posterior probability of a given b, is equal to prior probability of a P a into likelihood of b given a, which is P b given a, divided by probability of b. In Argmax based computation, when we are maximizing the function P a given b over all a's, P b is generally neglected because it is not influencing the relative ranking of different possibilities for P a given b varying over a. So, we have also remarked on why we would like to apply the Bayes theorem and work with P b given a and P a instead of P a given b. A very compelling reason for this is we can make use of the prior probability P a, which often acts like a filter to eliminate bad sequences for a given b, and it also is sometimes more convenient and more confidence boosting to work with P b given a. Okay. So, we will have examples to illustrate this point. So, let us get our fundamentals very clearly established. The reason for applying Bayesian decision theory is to be able to make explicit or clearly separate prior probability from clearly be in a position to make use of prior probability and the likelihood. Okay. So, we already discussed in the last lecture the part of speech tagging, and this will the whole mathematics and experimentation on part of speech tagging will be explicated in the next few classes. We will devote to at least 2 lectures on part of speech tagging to illustrate the methodologies of statistical natural language processing. Now, part of speech tagging was mentioned very briefly in the last lecture to bring out the main use of Bayesian theorem in part of speech tagging, and also to show an example of how a natural language processing task can be formulated as an Argmax based computation. The other 4 problems we would like to discuss in this lecture are statistical spell checking. This can be formulated as an Argmax based computation, automatic speech recognition, namely conversion of speech signals into linear text, probabilistic parsing, how do we obtain the best possible parse tree from a given sentence, and a statistical machine translation is how do we obtain the best scoring translation from one language to another. All these are sequence leveling tasks. We will see how, and all these are amenable to Argmax based computation and use of Bayesian theorem. So, part of speech tagging, the example shown was that a sentence has a number of words, and these words are given part of speech tag labels. These labels are obtained from the properties of the words themselves and the context in which they are embedded. So, the best possible tag sequence T star is obtained as argmax over T of probability of t given w. So, what is the input to the system? The input is nothing but the word sequence w. These t, w are not single entities, but these are sequences. Let us remember that t is the tag sequence, w is the word sequence. So, given the word sequence, you would like to find the best possible tag sequence, and this can be converted into probability of a word at a position I given the tag at that position t I into probability of t I, that is the tag at position I, given that the previous two tags are t I minus 1 and t I minus 2. So, this we remarked gives rise to a trigram based computation, and this kind of tagger would be called a trigram tagger. Okay. And there is a very famous system, a very famous part of speech tagger, which is based on hidden Markov model and makes use of trigram, called the TNT tagger, TNT tagger. Okay. So, this is the heart of all these taggers, and we will also see how these computation can be modeled by the very well known and famous combination of hidden Markov model and Viterbi decoding. So, the formulation is through HMM and Viterbi computation. Let us now look at another example of natural language processing, which is spell checker, and in the spell checker problem also we will apply Bayes rule. So, the problem is as follows: W star equal to Argmax P W given T. Okay. So, many times we do not explicitly mention what the Argmax is over, because of the advantage of the notation shown here. W star, star is the best possible, W star, star indicates best. So, best possible W is W star. And how do we obtain this? We obtain it from amongst a number of W's, and for each W we can obtain the P W given T value. Okay. So, T is the misspelt word as is shown here, and W is the correct word corresponding to T. So, W star, the best possible word corresponding to the misspelt word T, can be found by an Argmax computation over W of the probability of W given T. Now, we apply Bayes theorem here, and we obtain the expression Argmax P W into P T given W, where W is the correct word and T is the misspelt word, as has been mentioned already. Now, the question that arises as before is, why should we apply Bayesian rule here? And this boils down in part to answering the question, what should we be finding, P W given T or P T given W? Okay. So, here we would like to again remark that this P W, which becomes explicit through the application of Bayesian rule, indeed acts like a filter. Okay. So, P W is a valid is a character sequence producing a word, and the probability of the character sequence goes high when it is an actual word in the language. If the character sequence does not correspond to an actual word of the language, the P W value is low, thereby making that W star score also low. Okay, that particular W score also low. So, therefore, what is happening is that the words which are not the character sequences, alphabet sequences which are not words of the language are eliminated because of the influence of P W. Okay. So, the probability indeed acts like a good filter. Okay. So, the other question of course is it easier to compute P W given T, that means probability of the correct word given the misspelled word, or is it easier to compute the probability of misspelled word given the correct word. Okay. So, now we make some assumptions and we come back to that question little later. We make some assumptions. So, these assumptions are the following: T or the misspelled word is obtained from W, the correct word, by a single error. Okay, by a single error, and the words consist only of alphabets. We are dealing with only alphabetic sequence which are words, and this discussion is primarily from another famous textbook of natural language processing written by Juravsky and Martin, Speech and Natural Language Processing, which is a well known book. Okay. So, now let us make some remark on the formulation of the problem. First thing to notice is that spell checking is looked upon as an Argmax computation. Okay. Why Argmax computation and why probability? Probability, let us understand, is a very powerful mechanism to produce a ranking on a set of entities. The probability values associated with these entities give a score for these entities, and that inherently produces a natural ranking for the entities, and based on this ranking we choose a particular entity. So, in this particular case of spell checking, given the misspelled word, there are a number of possibilities for the correct word. Okay. If I look upon the misspelled word as a sequence of characters, then a changed character sequence is what we are looking for. Okay. After all, the corrected word from the misspelled word, what is it? It is nothing but a transformation of character sequence of the misspelled word into the correct word, and many options are available. We have to choose one amongst them. How do we choose? We choose based on a rank. Where does the rank come from? The rank comes from the score associated with a character sequence, and that score is nothing but a probability value. Okay. So, see the whole line of reasoning. It is a pretty intuitive sequence of steps. So, now if we look at the slide again, we find that W star is obtained from Argmax P W given T. Now, these assumptions that T is obtained from W by a single error and the words consist of only alphabets, these are the assumptions which essentially give rise to a method by which these probability values are calculated, and the method by which the best possible character sequence is found as a possible candidate, the correct candidate for the misspelled word. Okay. So, since there is only a single error in the misspelled word, okay, removing that particular error should give rise to the correct word, and there are 4 kinds of errors giving rise to 4 valuable data structures called confusion matrices. So, if x and y are alphabets, then we define the function sub x y equal to number of times y is written for x. This is substitution. Ins x y is the number of times x is written as x y. So, y is inserted after x, that is why it is called the ins function, ins x y. Del x y is the number of times x y is written as x, that means the number of times y is deleted when it is preceded by y, and trans x y is the number of times x y is written as y x. Now, these functions, where do they come from? These functions come from the actual experience of people in spell checking situations, what happens is that people make this kind of mistake of substituting a character x, an alphabet x, by y. Okay, this is a common spelling mistake. We will take some example. People also make the mistake of writing y after x. Maybe that is an accidental press of the finger where on a button which is adjacent to the button for x. So, for example, if I look at the keyboard, I find that G and H are adjacent to each other. F is also adjacent to G before coming before G. G is again flanked by alphabets T, Y, V, B and so on. These are neighbors of G which are seen from the keyboard. I will just draw it for the sake of convenience of discussion. Okay. So, I find from the keyboard that we have G here, then H, and then we have F here, and G has on top of it the alphabet T. It also has a part of the Y button, and then I find that it has these two buttons V and B. So, therefore, it is quite imaginable that when a person is typing G, his finger can also touch some finger can also touch T, Y, B, H, V or B or F, and therefore, an insertion can happen after G. So, one might also question that why is it not happening before G? We can see that after or before does not matter, because both the situations can be captured by either after or before. Okay. So, in insertion error in x y, an example of this error would be somebody is trying to, let us say, type fight G H T, and instead of that types it as F I G B H T, because B happens to be adjacent to very close to B and a finger has touched B. So, B has come in. This is an insertion error where x is replaced by x y. So, G is actually replaced by G B. So, this is an insertion error. Let us take other examples where other kinds of error mentioned are present. A very important error is sub x y, where x is substituted by y, x is substituted by y. So, if I take the word apple for example, apple can be misspelled in the following way. For P, I might just type O. So, A O P L E, which is a wrong word. So, this P has been substituted by O. Okay. And this is an example of sub x y, substitution of x by y, P by O. Then we have the error of deletion, which is del x y, and in this case the error is that x y is written as x. So, a sequence x y has become x. So, y got deleted. So, instead of writing apple A P P L E, you might write this as A P P E, where this L has been deleted. Okay, L has been deleted. So, this is an example of del x y. Another very common error is trans x y. The number of times x y is written as y x, or x and y are transposed. So, for apple, of course, transposing these two p's will not make any difference. However, if we have A P L P E, here what is happening is that this P and L are getting transposed between them. So, P and L are transposed, and therefore, A P P L E has become A P L P E, which is an error. So, these are the different types of error for spell checking, and these are the 4 errors which are assumed to be present in obtaining a misspelled word. This is an assumption. Okay. We do not have 2 errors committed in the character string. When you are typing a word, we are making at most 1 error. This is an assumption. So, from these we come to these functions which are useful in our probabilistic computation. So, sub x y, number of times y is written for x, substitution. Ins x y, number of times x is written as x y, insertion. Del x y, number of times x y is written as x, deletion. Trans x y, number of times x y is written as y x. From these confusion matrices, we could obtain the probability of P t given W in the following way. P t given W is equal to P t given W s, that is substitution kind, plus P t given W I, that is insertion kind, P t given W d, deletion kind, plus P t given W x, that is the transposition kind. So, the probability of obtaining a misspelled word t from the correct word W is the probability of these mutually exclusive 4 events of substitution, insertion, deletion and transposition. Okay. Whether these events are actually mutually exclusive or not, that question of course arises in the mind, but since we have made that assumption that each misspelling is a result of one and only one of the 4 errors of substitution, insertion, deletion and transposition, we can write the probability of t given W is nothing but the probability of t given W through substitution error plus probability of t given W through insertion error plus probability of t given W through deletion error plus probability of t given W through transposition error. Okay. So, P t given W of S kind, that is a substitution kind, is nothing but substitution of x by y, the number of times x is substituted by y divided by count of x. Similarly, insertion probability is given as ins, the number of times x is written as x y divided by count of x. Probability of t given W through deletion is nothing but a deletion probability, that is the deletion count of x comma y, that is the number of times x y is written as the number of times x y is written as y divided by count of x, and P t given W of transposition kind is the number of times x and y are transposed. Number of times we write y x in place of x y divided by number of counts of x. So, these are considered to be mutually exclusive events, and through these substitution counts and count of x and so on, we obtain the probability values given here, and from this it is possible to compute the probability of t given W. Okay. So, now we come to an interesting question about the other part of the probability, and we now look at the expression through our writing. So, W star was written as Argmax W over W, P W given T. Okay. So, now this was converted into Argmax P W into P T given W over W. Okay. We have already discussed how to compute P T given W. This is already discussed. Now, we go on to discuss P W. So, P W is nothing but the probability of W. So, the issue here is what is the probability of a particular word. So, let us see the probability of apple for example, as a word is equal to the number of times apple occurs divided by number of all words of English. This looks like a reasonable probability measure. So, probability of apple is equal to number of times apple occurs divided by total number of words of English, total number of words of English. Okay. Now, the moot question here is what is the meaning of number of time apple occurs? Where does it occur? Okay. So, this brings us to a very important point about what is called the corpus. Corpus. Importance of corpus is supreme in NLP. So, in natural language processing, the importance of corpus is indeed supreme. It takes the center stage in all kinds of computation. And what is the meaning of corpus? Corpus is nothing but a collection of documents expressing coherent text. Okay. So, we collect documents in textual form on many topics from many sources and we put them together, we make a collection out of it. So, this particular collection is called a corpus. Okay. Corpus is actually very important in whole of statistical natural language processing. Okay. What kind of corpus? The more variety in the corpus, we take corpus, we collect the corpus let us say from sports domain, from economics domain, from history domain, from science domain, from technical domain, we collect them, we put them together and this becomes a very important repository of language behavior of people. Okay. The corpus can be spoken corpus, where we collect the recordings of speeches, conversations, dialogues of people, and the corpus also could be in the form of written corpus, which are material available in textual form on the internet, in libraries in printed form or in some other collection. So, basically collection of all kinds of written text. So, written text produces written text corpora, recording of speech, dialogue, conversation produces spoken corpora. So, let me mention two very important corpora of English which have been used heavily in natural language processing. Written text corpora, we have what is called the Brown corpus. You can Google on this and you will get all the information. Brown corpus. The other is BNC corpus. This is the British National Corpus. British National Corpus. Okay. So, these are very famous corpora. These about 1,000,000 words and this is about 10,000,000 words. Okay. So, we mentioned these two very famous corpora, and as far as spoken corpora is concerned, there is a famous one, spoken corpora. We have what is called Switchboard Corpus. Again you can Google on this Switchboard Corpus. This is essentially the record of telephonic conversation of people, and these are many hours of recordings, So, they provide valuable information on the spoken behavior of people. Okay. So, I hope I have explained to you the meaning of corpus, which is essentially coherent pieces of text. Just a jumbled collection of words is not corpus. Corpus stands for meaningful text. People's ideas, thoughts, people's mind are reflected in documents, textual documents, and a collection of textual documents forms what is called the corpus. So, when a machine is shown a corpus, okay, we do something with the corpus through a machine, we essentially expose the machine to actual language behavior of people, which is very, very important for natural language processing. So, we come back to now the question of spell checker, and looking at the transparency, we have said that the probabilistic formulation of spell checking is this: W star, the correct word, is nothing but argmax of P w into P t given W. Now, P t given W we have extensively discussed. P w we have said that number of times W occurs divided by total number of words. Now, total number of words where? Total number of words in the corpus, and the number of times W occurs where? Again in the corpus. So, do you get the methodology? The methodology is that to compute P w, we look at a corpus, okay, substantially large corpus, and see how many times a particular word appears. So, the probability of apple can be computed as the number of times apple appears in the corpus divided by total number of words in the corpus. So, the question that might arise in your mind is, when we say total number of words in the corpus, are we talking about unique appearances, the unique number of words? No, we are talking about the document length, the total number of words in the document, okay, and the total number of times the word apple appears in the document. So, this brings us to another interesting discussion, which is again a slight diversion, but let me all the same mention this, an interesting diversion. When we take a corpus, there are two concepts, tokens and types, tokens and types. So, tokens and types. Tokens is, so tokens are actual white space separated strings. Tokens are actual white space separated strings. Therefore, number of tokens in a document is equal to document length. Is it clear? So, tokens is the actual white space separated strings in a document, okay. And therefore, the number of tokens in a document gives us the document length. Having explained tokens, let me also tell you what types are. What are types? Types are unique strings in a document, okay. So, this means that it captures the unique words or strings in a document. So, let me take an example to illustrate this point. It is an important point in our computation. So, type versus token example. Suppose I take the sentence here, the man looked at the other man. This is the sentence, the man looked at the other man. The number of tokens, here is equal to white space separated strings. So, essentially the number of words here. So, 1, 2, 3, 4, 5, 6, 7, number of tokens is 7, which is equal to the document length, because the document has 7 words, 1, 2, 3, 4, 5, 6, 7. What is the number of types? That is the number of unique words here. The number of unique words will always be smaller than the number of words, So, the number of types is always less than the number of tokens. So, if you look at the sentence here, the man looked at the other man. The unique words are the man looked at other. Okay. The next the and next man, they have already appeared before. So, number of types is 7 minus 2, which is 5. Okay. So, this document, the man looked at the other man, has 7 tokens and 5 types, that is 5 unique words. Okay. So, this was a diversion and we go back to the discussion on spell checker. It has taken us some time, but it illustrates many fundamental and important concepts. So, in the slide we again see that W star is nothing but argmax P W into P T given W. We were discussing how to compute P W. P W is nothing but the number of times the word W appears in the corpus we have taken to compute the probability, divided by number of tokens in the corpus, not types, the number of tokens in the corpus. That means, the number of times apple appears, okay, divided by the document length, that is the total number of words in the document. So, now this makes it very clear how to compute P W. Now, what is the use of P W? The use of P W is that through this computation, through this argmax computation, the statistical system will suggest many possibilities of the corrected words. After all, it is a probabilistic situation, and the corrected word can be any sequence of alphabets. Okay. Now, we will choose that particular sequence of alphabets as the possible correction, which has the highest probability. Now, since it is a probabilistic situation and we are computing it through P T given W, probability of misspelled word from the correct word, P W is acting like a filter. Okay. So, the string apple APPLE has a high probability in the corpus. The string APLPE has lower probability, because this string does not appear in the language. Okay. We are assuming that the corpus is a set of documents where all the words are correctly spelled. Okay. So, now we can see that P W is acting like a filter. If the word is an improbable string in the language, P W value will be less, and that particular W will not appear in our suggested list of options. Okay. The probability value will automatically come down because of the P W quantity. Now, this P W as shown here is called a word model. Okay. This models the probability of an alphabet string being an actual word of the language, a valid word of the language. Thereby, it has this filtering influence. Okay. So, how these two probabilities are actually computed, how they are broken down, how they are again put together to form a string, all these are discussions which will become clear when we do part of speech tagging. But let us appreciate that we have understood first through pause tag computation how to formulate a problem as an argmax situation. Second, we have understood why Bayes theorem may be applied. Bayes theorem makes a prior probability explicit, and this prior probability acts like a filter. Okay. And the likelihood probability is always computed by means of independence assumptions and product of probabilities of smaller units. So, these are the principles. Okay. We proceed now, and we take an example which you can make use of as a possible assignment implementation. Here is an URL which is a database of misspelled words, www.wsu.edu/Bryans/errors/errors.html, or even http://en.wikipedia.org// wiki/Wikipedia lists of common misspellings for machines. Okay. So, clearly this second URL has been put in place by somebody who has been actually working on probabilistic spell checker. So, these are resources by which a probabilistic system can be trained to detect spelling errors in future, and those probability values can be obtained by processing the data given here. This kind of probability value computation is also called training. Here is a sample. Abandoned is written as abandoned here, which is the spelling mistake. N has been written as double N. Maybe the key has pressed the N key, the finger has pressed the N key twice. So, this belongs to the error of insertion type. So, N has been written as double N. Aberration ABERATION actually is correctly spelled as ABERRATION. Only a single R has been placed, that means the error is of I would say deletion kind, where double R has been written as R. Abilities is written as ABILTIES. This is a deletion error where I has been deleted from abilities. This ability ABILTY again is of a deletion kind. This I has been deleted. Abandon has been written as abandon, A has been written as O. This is an error of substitution kind. A has been substituted by O. Abandoned, this is abandoned, and again it is a substitution error. Abandoning, again a substitution error, A replaced as O. Abundance, again substitution. Aborigine is actually written as ABORIGINE, and here we see ABORIGENE. So, this is an error of substitution type. This is a substitution error. So, here we see mainly substitution, insertion and deletion errors. We do not see an example of transposition error, but if you look at the database, there would be such examples also. Here is an interesting point I want to bring to your notice. So, this particular text is doing the rounds in the internet. I received this through an email. Lot of people have obtained this through email. Now, this text is full of spelling errors. There is not a single word which is not spelled incorrectly, not a single sufficiently long word. I can see that I is correctly spelled, you cannot do much about it, and it is correctly spelled, it is correctly spelled, the is correctly spelled, but they are also misspelled. Okay. So, now we see that we can read this text quite conveniently. So, what is the first sentence? If you can read this, you have a strange mind too. This is the way the sentence is read, and this is full of spelling error, but looks like we do not have any difficulty in reading this sentence. Our mind is correcting the sentence as it goes on reading it. So, phi, I and F have been switched. This is a transposition error. U, YOU has been written as YUO, again a transposition error. Can, CNA, transposition error. Read these, transposition error. This is again transposition error. You have a strange mind too, strange, STRANGE. So, here we see there are two errors here, strange, and G has been deleted from here and G is placed here. There is an insertion error here. So, this is deletion and insertion both, but mostly the errors are of transposition kind. But the remarkable thing here is that we can read the sentences with ease. If you can read this, you have a strange mind too. Can you read this? Only 55 people. See how people has been spelled. People can. I could not. This is very, very wrongly spelled, but we can still read it. I could not believe that I could actually understand what I was reading. The phenomenal power of the human mind, according to a research at Cambridge University. It does not matter in what order the letters in a word are. The only important thing is that the first and the last letters be in the right place. So, this is a very, very interesting point, right. The rest can be a total mess and you can still read it without a problem. This is because the human mind does not read every letter by itself, but the word as a whole. Amazing, huh? Yeah, and I always thought spelling was important. If you can read this, forward it. So, this is a very nice and interesting example. The author says that the letters within a word do not matter as long as the first and last letters are properly kept. So, this is a very, very interesting issue. There are cognitive science points involved here, and with that we finish today's lecture. We will take up other natural language processing problems, but I leave it for you to reflect on how much powerful the human mind is when it comes to deciphering the correct meaning in language situations. This is extremely fault tolerant and extremely resilient to noise.